Okay, thank you. So it's a pleasure to be here, and let me thank Avi for the invitation and all of you for participating. And feel free when you have questions to unmute yourself or to use the chat. I don't really see the chat, but I think I can look at it. So if Tony will tell me when there is something in the chat, I'll try to look at it.
Yeah, no problem at all.
Okay, good. So so I'll be talking about splitting necklaces, existence, hardness, and approximation. And the new results are a joint work with Andre Grauer, who was in last year an undergraduate student in Princeton, and now is a graduate student in Stanford. So before I tell you the statement and something about the proof of the basic result, let me give you if I manage to give you here two titles of two YouTube presentations of the result and in some aspects of the proofs, and I also checked the number of views of these YouTube pieces a few days ago, and here is the statement of the necklace theorem, which will be the topic I discuss, and in this form, so a special case of k equals 2 was first proved by Goldberg and West, and then we found a very short proof, and the version that I described here is a generalization, and it says the following. So suppose we have a necklace and we open it at the clasp, so it's just an interval of beads. And suppose for simplicity that the number of beads is divisible by k, the number of beads of each type. So we have altogether n types of beads and k times ai beads of type I. And the claim is that we can always make at most k minus 1 times n cuts, and then we will get k minus 1 times n plus 1 intervals, and then it will be possible to distribute the resulting intervals into k collections so that each collection will be exactly fair. It will contain exactly ai bits of type I for every I between 1 and n. So one way to think about it, and this is the way to remember what it says, is that we had this group of k thieves, and they stole together a necklace, and they want now to split it fairly among them, and they wanted that each of them will get the same number of beads of each type, so the same number of diamonds and rubies and sapphires and so on. And they want to do it by a small number of cuts because maybe the wire is also expensive, or maybe it's hard to make a cut. So the claim is that they can always make k minus 1 times n cuts and distribute the intervals fairly. And it's easy to see that this k minus 1 times n is tight, because you see if the beads of each type appear contiguously on the necklace, then just to ensure that every thief will get a positive number of beads of each type, we have to have at least k minus 1 cuts inside the interval of diamonds, and at least k minus 1 cuts inside the interval of rubies, and so on. So altogether, we need k minus 1 times n cuts. And the claim is that we can always do it. So the early motivation or kind of questions of this type were first considered by Steinhaus, who considered the cake cutting problem. It's not exactly this, but it's closely related, So he wrote about it already in 49. And in fact, even long before that, before he was interested in splitting cakes, he was interested in cutting ham sandwiches, which makes sense that you leave the dessert to the end. And already in 38, he posed the ham sandwich theorem, and this was posed by him and solved by Banach, and it's also a result of the same flavor, and actually, as I mentioned later, it's really closely related to this necklace, at least for k equals 2. Okay, so I want to say something about the proof, just the steps of the proof. So there are two simple steps and one that requires a little bit more work and is less constructive. And so here are the steps. The first one is really an observation that if we know the result for a group of K1 thieves or K1 collections, and we know it for K2, then we know it for K1 times K2. And this basically follows by first splitting it evenly to K1 collections, and then each of these collections you split to K2 collections, and somehow the function that tells us the number of cuts, this K minus 1 times n, has a form that if we do it, then the number of cuts turns out to be the same, right? This is not true for any function, but here it works. So this is one step that is very simple. Now here is another short step. We want to transform the problem into a continuous one. So what we do is we change the necklace into an interval colored by n colors. Whenever we see a diamond, then we replace it by a small segment colored blue, maybe. And when we see a ruby, then we replace it by a small interval colored red. And this defines basically n probability measures on the segment. And in fact, we can even forget that they have disjoint supports because the continuous result holds for any probability measures. And then the main step is to prove the continuous version. And this is by applying some fixed point theorem. So specifically in the original proof, what is used is a result by Baran, Schlossman, and Such. But there are some other known extensions of Borsuk-Ulam theorems that can be used as well. And one interesting point is that a topological result holds only for prime numbers k. It's just the topological result is not true, in fact, for non-prime k. So it is lucky that the first step tells us that it's enough to prove it for primes, because if we know it for two cardinalities of the size of the group of the thieves, then it's true also for the product. And besides that, only groups of prime numbers of thieves would have been possible. So this is basically the statement, something about the proof. And one feature of the proof is that it's not constructive. It does not provide an efficient algorithm for finding the k-1 cuts that we know that exist. It is a question that intrigued me for a long time. If we can find these k-1 cuts efficiently for a given input necklace, and this is interesting not only for the algorithm, but maybe for understanding if indeed the topology is essential. So somehow the feeling is that if we find maybe a more combinatorial or another proof of the result, then maybe it will be more constructive. Okay, so and because I want to consider the algorithmic aspects of the question, let's also consider an approximate version, and this is what I call here epsilon approximate splitting. So we're given an input necklace, again, beads of n types. And what we want now is to use a small number of cuts, and we want to partition it into k collections, so that now each collection is not precisely fair, but maybe each collection contains a fraction of at least 1 minus epsilon over k, and most 1 plus epsilon over k of the beads of each type. And the examples that I mentioned, the simple example when the beads of each type appear contiguously, tells you that for any epsilon that is smaller than 1, even if you just want to ensure that every collection will get a positive number of beads of each type, then sometimes you do need k minus 1 times n cuts. So we cannot, in general, gain in the number of cuts, but hopefully this question is maybe simpler algorithmically. And I should say, by the way, that for simplicity, I assume that the number of beads when we want a perfect splitting is divisible by k in each type, but you don't really have to assume it. If it's not divisible by k, then there is always a partition in which each one gets either the floor or the ceiling of the number of beads of the corresponding type divided over k. And this is by somehow using the integrality of network flow and inserting it into the proof. Okay. So, these are this is a statement. This is the algorithmic question, and let me ask if there are any questions.
I'll ask one question. How hard do you expect it to be to actually solve the necklace problem exactly algorithmically? Is it similar to making algorithmic all the applications of Null-Stolen sats? Is it what? Is it p-pad? Is it NP-hard? What is it?
Very, very good question. So this is my next slide, exactly. So let me move to the next slide, and let's talk about hardness. So here is something that tells us about hardness. So of course we know in complexities that we do not really know to prove lower bounds for any interesting problem, but what we do instead usually is to prove that problems are hard for some complexity classes, like problems are NP hard or problems are PPA hard. So this is a statement here. And this was proved a few years ago by Aris Philos-Pratsikas and Paul Goldberg, and then in another paper with Fredrickson and Zhang. So I'll not talk too much about these complexity classes, but complexity classes PPA and PPAD were introduced by Christos Papadimitriou in '94. And they have to do with the problem of finding solutions to problems that always have a solution and for which checking that a solution is indeed a solution can be done in polynomial time. So this question is of this type, and PPA, the initials come from a parity, polynomial parity arguments, and the D stands for directed. And these are some specific complexity classes of this type. They are all subclasses of what is called the TFNP. And PPAD may be the best known problem that belongs to PPAD and is PPAD complete, is finding a Nash equilibrium in a game of 2 or more players, and this is known to be a PPAD complete. So the result here is that for k equals 2, so just 2 thieves, we want to split the necklace into 2 parts, then the problem of finding an epsilon approximate splitting even, so even not for epsilon equals 1, using the minimum number of cuts, so n cuts, here k minus 1 is 1, so k minus 1 times n is n cuts, n epsilon that is inverse polynomial in n. So this is PPA hard. Namely, if we can do this in polynomial time, then, for example, we can find a Nash equilibrium in polynomial time. PPA is a little bit bigger class than PPAD, so so it's okay. And there is a similar, stronger result, which is PPAD hard, if even if epsilon is some small fixed positive constant. Okay. So this suggests two questions.
Just the question, is it in PPAD?
Yeah, so it is in PPAD, right? Yeah. Right. I think because it's equivalent to a Tucker. Okay, let me say that I think, but I may be, I may be wrong. So it's definitely right. Yeah, yeah, it's definitely PPAD hard or a okay.
Yeah. So Ryan says should have said complete and not hard then.
Yeah, this is
so
true.
I
wonder why I wrote
PPA,
right. Yeah. So I wrote hard. Right. Yeah.
Cool.
Yeah, I think that's the beginning. Right. Yeah. Okay. Okay. Any other comments, questions? I can look from time to time to chat. Yeah. Okay. Good. So here are two questions that I want to consider. And one of them is, what can we do efficiently with more cuts? So maybe we cannot do n cuts. And in fact, their hardness result applies even if we allow a little bit more than n cuts, n plus root n, for example. But maybe if we allow n log n cuts, or if we allow something big constant times n, maybe we can do something. And then can we prove any unconditional hardness result, maybe in a restricted, in natural restricted model? So when we are not.
So what do you mean by more cuts? I mean, I know what you mean by more cuts, but why?
Yeah, maybe instead of n, I want to allow n square cuts or something. Okay. So, right, because it's not, I should say that it's not obvious at all that by using any number, so before we know the topological proof, it's not clear at all that using any number of cuts that is only a function of n and k and not a function of the necklace, that can be very complicated, we can get a fair partition or even an epsilon fair partition for some small epsilon. So we want, okay. And right, so actually something in this direction was known even before the topological proof. So Butt and Lighton were interested. They actually came to this problem for some VLSI circuit design motivation, and they had to prove something. So they needed to get some version for a. And what they proved is that for k equals 2, let's say, and for fixed epsilon, then there is a solution doing something like 1 over epsilon to the n cuts. So again, remember that the necklace can be very complicated. And a priori, it's not clear, even if epsilon is 1 over 10 and n is 5, that there is any number of cuts that will give us such a partition. And,
right. I have to ask the question again, or maybe I'm out of it, but so do you mean like one robber now gets more than one piece, or?
I mean, always, sorry, so even in the original one, every robber or thief gets more than one piece. He gets several intervals.
Oh, right, okay, gotcha.
Right.
Okay. So now I see.
Right, but we allow him to get even more.
I see. So there's a trivial.
By the way,
yeah. So there's just a trivial solution where you just each bead is its own cut or something dumb like that.
The trivial solution, is to cut it to single beads.
Yeah, gotcha. Okay, thanks.
And it's true that in some other versions of cake splitting or necklace splitting, we only care about fairness, so we don't want a completely even partition, then we insist on each one to get one interval, but then we get something else. So I'm not talking about this. Okay. So we really need, everyone needs to get.
I have another question. I have another question.
Uh-huh.
What happens if you use something that's not a circle? Like, I don't know, I use a torus, and the cuts
Right,
have to be.
yeah. So there are some results for a multi-dimensions where we allow, say, we have a torus and we allow vertical and horizontal cuts.
Yeah.
And some of the results extend, but I'll talk only about the interval now. But yeah, but there have been there are some results about higher dimensions, and basically the topological proofs extend.
Okay.
Good. So we had these initial results, and I mentioned another one where they care about some truthfulness or fairness. So let me not discuss it, and I'll consider also an online model because this is where the lower bounds will be proved, and I think it's natural, although one can argue about it. But anyway, here is a model. So we have n, k, and epsilon. Epsilon may be 0, and we know in advance the number of beads of each type, okay, and therefore the length of the necklace. But now we get the beads one by one. And whenever we see bead number t plus 1, we have to decide immediately if we want to cut before it or not. And if we make a cut, we have to decide to which fifth the resulting interval goes. Okay, so this is an online model, and the question is what we can do here. And let me tell you something about the results, and then I'll try to describe some proofs, which I think are interesting. I'll try to convince you. Now I'll state the results only for k equals 2, so only for 2 fifths. But basically everything extends to general k. It makes things a little bit more complicated to state and a little bit more technical, but the ideas are very similar, so we'll do everything for k equals 2. So here is the first result about an offline algorithm for epsilon halving. When k equals 2, we'll call it halving instead of splitting. So if we want to solve the epsilon approximate necklace halving with beads of n types efficiently, deterministically, this can be done with n times 1 plus log of 1 over epsilon cuts. Okay, so if, for example, epsilon is 1 over 100, then maybe this is 8 times n cuts. And remember that for small fixed epsilon, the problem is PPAD hard. I still say hard because I'm not completely sure about so if we want n cuts, then it's hard. If we want constant n cuts, then we can do it. So this will be one result, and the corollary of it, and basically just by taking epsilon to be 1 over the number of beads of each type, and it says that the necklace halving problem with beads of n types, with at most m beads of each type, can be solved precisely with at most n log n plus 2 cuts. Okay. So still there is some dependence here on the length of the necklace, but only logarithmic dependence, and that's the best that we know to do efficiently. This is one. Now, here are the results about the online case. Let me actually show everything. So if we want to do it online, and we have n types, then we can do it efficiently, deterministically, and online with at most up to logarithmic terms, n over epsilon square cuts, which also means that everybody gets that many intervals. And this is essentially tight for every n, which is at least 3, up to the logarithmic term. Okay, so online you really need n over epsilon square types, and actually if you go back to the precise cutting, then exact online halving, then I wrote here just a special case. So suppose we have beads of 3 types, just 3 types. K is 2, right? So we know that we can solve it precisely with 3 cuts. But if we insist on doing it online and the number of beads of each type is m, or at most m, then we can do it with something like m to the 2/3 cuts, and this is tight. So really online things become much harder if those thieves for some reason will insist on doing it online. They will need a huge number of cuts, even if their number is if the number of types of beads is small.
Sorry, what is exact referring to over here?
What is exact?
Yeah.
I didn't hear.
What is exact referring to over here?
So exact means that I want that each one will get exactly the fair 1/2 of the beads of each type.
Ah, okay, thank you.
So exactly 1/2 if it's divisible by 2, and let's say up to 1 if it's not divisible by 2. So this is exact, right?
Noga, does it make sense to have?
We're having trouble hearing you, at least I am.
Yeah, I heard.
Sorry, let me repeat the question. Let me repeat the question. If the look ahead in the online is more than 1, if you can see 10, we can see log n, does it make sense?
Yeah, you can look at that. It will not change things by much. So if you can see 10, then it's still m to the 2/3 and the constants change. And if you can see log, it will affect a little bit, but it doesn't help much. So really having a look ahead, which is not really linear in the length of the necklace, will not help much. Okay, and good. So I want to try to describe some proofs, and what I'll do is that I'll show one positive and one negative, or one upper bound, one lower bound. So the first one will be an algorithm. I'll really show it. It's simple enough that I can describe it. And this will be an offline epsilon halving, and then I'll kind of outline one of the lower bounds. So here is what I want to describe now. So what I call this, it's called offline epsilon halving. We have this necklace, and we want to partition it into 2 roughly equal collections. Each one contains between 1/2 plus epsilon and 1/2 minus epsilon of the number of beads of each types, n types of beads, and we want to do it efficiently with n log of 1/epsilon cuts. And so this will also prove, I mean, if we forget that we know the exact result, the topological result, this will also prove that there is such an epsilon halving with that number of cuts, and it will be efficient. So let's see how we do it. So we first replaced each bead by a small interval of its color, getting n probability measures on 0, 1. As you see in the picture here, you have this red probability measure, and we have the yellow and the blue probability measure. We have n of them. Okay. And what we want to do, maybe I would say it already here. So we want to cut to 1/2 or approximately 1/2 these probability measures. And of course, maybe some of the cuts that we'll have will be in the middle of small segments that correspond to beads, but there is no problem to round it later. So really, we can basically forget that this comes from the specific beads. Now, for any interval, we have an interval in 0, 1. then we have the measure of this interval according to all these probability measures, okay? P1i, P2i, up to Pn sub I. And we define the sum of these measures. So that's another measure. The total measure of I will be the sum of the small measures of all of them. As I said, I can forget now that the probability measures came from the beads, so I will not use really the fact that they have disjoint supports, but okay. So this Pi is defined. And what we do now first is that we split the interval 0, 1 into 2n smaller intervals, and each has P, this total measure, exactly 1/2, right? The total measure of everything is n, because it's the sum of n ones, and I can split it to 2n equal parts. You can convince yourself that, of course, with the beads, we can do it exactly, and indeed, maybe some of the cuts are in the middle of intervals corresponding to beads, but we don't care about that. And for each small interval like that, j, we denote by vj the vector of length n, which gives us the measure of j according to each of the n measures. So this is a vector. And what we really want to do, so we just want to find a collection of not too many disjoint intervals. This is what thief number 1 will get. And what we want is that the sum of the vectors corresponding to these intervals will be as close as we can to the vector half, 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 right? Because if it's exactly the vector of half, it means that everyone gets the collection contains exactly half of the measure of each type, and the L infinity norm measures how far we are from this ideal partition. Okay, so we want to, basically, we have a fractional solution, right? So this H is a sum of half times all these vectors, and we want to round this solution really to change all the coefficients to 0 and 1. So this is similar to kind of things that people are doing in discrepancy or in rounding fractional solutions, and we'll try to do something similar. Okay, so we will, during the algorithm, we will maintain an expression of this vector h, exactly the vector h of half, 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 as a linear combination of vectors vj for disjoint intervals j, where the coefficients will be in the closed interval 0, 1. Okay, so if a coefficient is already in the boundary, it is either 0 or 1, then we declare it fixed. We will not change it anymore. If it's 1, the interval will go into the collection. If it's 0, it will not. And if it is in the open interval, we call it floating. And we'll keep changing the floating coefficients and fix them one by one, but also from time to time, we will keep splitting intervals to subintervals. So let's see how we do that. So I wrote here by standard properties of basic solutions of linear programs. So this is some simple linear algebra. H, that is a linear combination of the vectors vj that we started with, right? It's half times all these vectors. We can express it as a linear combination of these original 2n vectors, where at most n of them are floating. And this is just linear algebra. I mean, we look at these vectors, as long as vectors with floating coefficients, there are more than n of them, we find the linear dependence between them, and then we add or subtract some constant times this linear dependence until at least one of the coefficients becomes fixed, and still keeping all of them between 0 and 1. So this is simple to do, and to do so, we just have to solve some linear, homogeneous linear system of linear equations with n variables and maybe more than n vectors. So this is definitely efficient. And now we fix such a representation. So now the number of floating coefficients is only at most n. And then each floating coefficient, we take the interval and we split it into two equal parts. Remember that the interval had a total measure of half. Now we split it into two intervals, each having a total measure of a quarter. And we keep the same floating coefficient for both parts. So still the linear dependence gives h. And now we can shift the coefficients again, because now we will have again 2n floating coefficients, because each one was split into two. And then we'll shift them again until at most n of them are floating. And we'll keep doing it. So if we repeat this process, some log of 1 over epsilon times, then we will get an expression of h as a linear combination of at most n times log of 1 over epsilon plus 1 maybe intervals, because we do it log of 1 over epsilon times. Each time we add n intervals. And now each p measure of any of the small intervals with floating coefficient is at most epsilon over 2. So we make sure that it is small enough.
So Noga, this is very similar to the proof of Beck-Fiala, for those of us who know it.
That's right, yes.
Okay.
So similar to right. And
you're going to round them off at the end.
The difference is that we keep splitting intervals to right. So once okay, yeah, but it is similar to techniques in discrepancy theory. And from now on, we are not going to add cuts at all, but we'll keep changing the coefficients still, right? So we have these n floating coefficients, but now the p measure, the total measure of every interval with a floating coefficient is very small. So since the sum of these total measures of the remaining intervals is at most n epsilon over 2, we have n intervals, each of them with a measure epsilon over 2, then there exists an index I so that the sum of the pi measures of these intervals is at most epsilon over 2, right? Because there are n pi's. And when we look at this I, we don't have to worry about it anymore, because no matter how we will round now these floating coefficients, then the ith measure will be okay. It will be within epsilon over 2 of what it should be, because we are only changing numbers that are between 0 and 1 to either 0 or 1, right? So this guy, the measure I, will be okay no matter what. So we can forget about it. If we forget about it, then the vectors now are of length n minus 1. Okay, but we have n of them maybe, so again we can find a linear dependence, we can shift it, and we can fix some interval, and we repeat it, and the process terminates, so the vectors become smaller and smaller. I mean, we keep forgetting coordinates, and at the end we are left with a vector of length 1 whose unique component is less than epsilon, in fact epsilon over 2 as I wrote it, and then we can include or not include it in our collection as we want in order to round things. And now we have to round the cuts that lie inside the beads, and we can only gain something like this, right? Because we would only give every such bead to the guy who needs it more. So this is basically everything. We get the collection of these joint intervals, some of the vectors corresponding to them in the L infinity norm is within distance epsilon over 2 of h, which is exactly what we wanted. And as we observed during the proof, the only things that we've been doing are solving some more basic linear algebra manipulations that are all efficient. So this was simple enough, and I could really show basically all the details. Are there any questions about this? Okay, so let me now say just something about a special case of the lower bound. So this is what I stated before is theorem 4. And this is for exact online halving. So again, we get this necklace. Now we get it online. And we want to split it exactly. We have 3 types of beads only. And we have m, let's say exactly m, or at most m beads of each type. Let me say exactly m for the lower bound. And we want to show that we need at least constant m to the 2/3 cuts. And as I said, this is tight up to a constant factor, although I'll not talk about the upper bound. So let me show you the basic idea here. We need a very simple rounding lemma, but I state it because there is some nice extension by Tiedemann that I want to mention. So suppose you have a real number p, which you can view as probability, so it's a number between 0 and 1. Then the claim is that there is an infinite binary sequence of 0s and 1s, so that the number of 1s in every, is it what I wrote is not completely right. So the number of 1s in every initial, I think it has to be initial interval, but anyway, no, it would be okay, right, yeah, sorry. So the number of 1s in every interval of the sequence is very close to p times the length of the interval.
Noga.
Yeah.
Does the BD sequence work? So
right, yeah, I'll mention it in a second.
Sorry. Okay, I think I'm
right, so what we want is that the number of 1s in every interval of length j is very close to p times j. Namely, it's either the floor or the ceiling of p times j. So it deviates from what it should be somehow by less than 1, okay, or by right. So here is, so I wrote one proof of this. I mean, if p is irrational, then there are things that are called BT sequences, and you can use them, and they give you really an explicit expression of this thing, and then you have to think a little bit what you're doing when p is rational. But for general p, one thing you can do is that you can just observe that by compactness, it's enough to have a finite sequence of length n, and then you can write it down as a linear program and use the fact that just this linear program, the matrix of coefficients here is totally unimodular. And because there is a solution which is just p everywhere, right? Each xi equals p, there is a real solution, then there is also an integral solution, and this will give us this sequence. As I said, there is a nice extension by Tiedemann, and we don't need it here. Definitely not for this special case, and this is less trivial. So this is when we want not a binary sequence, but we want maybe a sequence of integers between 1 and 10, and we have different probabilities for this 1 and 10, and we want that in each interval we will have, or at least in each initial interval, we will deviate by less than 1 from what we should get if we would have used the fractional solution. So hopefully this was clear. And in fact, it's the same for what I said here. the same holds even if you have different PIs for the different xi's, right? So they don't have to all be equal, but this is, okay. So it means that every real sequence we can approximate here well by some integral sequence of zeros and ones. Okay, so, okay. And now we want to show the lower bound. So it will be some adversarial argument. We will present the necklace bead by bead, and we'll decide what to do according to the cuts made by the guy who is making the cuts. Okay. So we present at the beginning only beads of types 1 and 2. Okay. We leave type 3 for later. And I still didn't say how many beads of type 1 and how many of type 2. But during the process, let me denote by X the difference between the number of type 1 beads of agent A of the first thief and the number of type 1 beads of the second one, of agent B. And similarly, Y will be the difference between the number of type 2 beads of the first one and the number of type 2 beads of the second one. So the first thing to observe is that if at some point the absolute value of X, namely the difference between the number of beads of type 1 that the first guy has already and the number of beads of type 1 that the second guy has already, if this difference is big, it's bigger than m to the 2/3, then from now on, we can force many cuts by distributing the remaining type 1 beads in all type 3 beads uniformly, essentially, using the rounding lemma. So if I would have been allowed to do fractional things, I would say that from now on, every bead is kind of fractionally green and fractionally blue, and I would split it evenly. And if I would have been able to do that, then you see that no finite number or no number of cuts would be enough to balance things eventually, right? Because at the moment, the guy has more blue, the first guy has more blue than the second guy. So altogether, he would have to get more beads than, or less beads than the other guy. And then the type 3 measure would not be distributed evenly. But of course, with discrete things, we cannot do it, and there is always a solution because we can split everything to single beads and allocate them to the required agents. But what we do is that we'll distribute it, we will use a rounding lemma, and we will distribute it imitating this uniform distribution. And then it's clear that we need many cuts, right? Because whenever you take a long interval, then essentially it gets the uniform parts of type 3 and type 1, and it will not be able to balance things. So if you work out the computation, it will show that you must have at least some constant m to the 2/3 cuts in order to balance things. Okay. So this tells us that we are not allowed to have a big difference between the number of beads of each type that the two agents get during the process. We have to always maintain it more or less balanced between the two. And now we have to choose, we choose some potential function. So let me choose this potential function. For this case, this one is good, x squared plus y squared plus this constant 3m to the 2/3 times x minus y. I should say that the normal potential function is x squared plus y squared, is somehow the L2 norm of the differences. But you need some correction. You'll soon see why, because in order to keep this potential function increasing. So the idea is that we want to give the beads in such a way that will force the potential function to increase. And if it will increase enough, then assuming that we don't do a big number of cuts, then X or Y will have to be big. And we already saw that if one of them is big, then we can force a big number of cuts. Okay. So this is a potential function. And then
Noga, can I please return you 2 slides before when you said that you're using the rounding lemma, then it's not an infinite sequence, right? You need to distribute some M type 3 beads and some M minus M to the 2/3.
That's right, yeah. So it's a finite sequence, but what's the question about it?
So in the rounding lemma, you're not getting, if you need P to be something, you're not getting, you can't be getting.
The rounding lemma, I am not ensured that the number of beads of each type is exactly the number that I want.
Yes.
Yeah, but this is not a problem. So I take this infinite sequence, and if I have to, then I just fix the last 3 or 4 beads in it, something, right? Because it is very close to being uniform all the time. So at the end, I'm correcting it. But it's true that I cannot take this infinite sequence as it is. Actually, another reason why I cannot take this infinite sequence is that my model is that I choose to do a cut after I saw already the next bead. So I'm already forced what the next bead is. And if I want to allow you to see 10 beads, I'm already forced about the identities of the next 10 beads. But again, it will not change much. So it will, on long intervals, I will still be okay. But it's true that I have to be a little bit careful here. Okay, I see that actually there is something on the chat. Okay.
Yeah, I think that was old.
Okay, but this is not the question. Okay. Good. So now we are given the values of x, y after a cut. And after a cut, I want to distribute the type 1 and the type 2 beads proportionally to the vectors that I wrote here. So these vectors that I wrote here. Now I wrote everything here is a polynomial, so everything is simple, but I wrote it here because I want to say what is happening with general potential functions. So the important thing about this vector is that it is orthogonal to the gradient of this potential function.
Sorry, Noga, wait, just give 1 second here. So this vector, do you mean the first part is for type 1 and the second part is the?
That's right, yeah. So the type 1 will be some product of the first coordinate and the type 2, right, yeah. Yeah, so if we choose this vector to be orthogonal to the gradient of M, because this M is sort of a convex function, then when we add this, so the next time that the algorithm will decide to make a cut, then he takes this segment and he gives it either to agent 1 or to agent 2. And what this corresponds to in terms of x and y is that he either adds the vector to xy or subtracts the vector from xy. And if this is orthogonal to the gradient, then kind of the main change in m of xy will be 0, either when we either add or subtract, and we get only what comes from the second term in the Taylor expansion, if you want. I mean, here it's a polynomial, so it's just a second term. And therefore, this will mean that always it will add something to the potential. Now, because of the rounding lemma, it's not exactly, right? Because this is not a exactly proportional to this vector, and but basically what can be shown is that this always increases mxy by something. I'll soon say it. But let me just stress here that indeed maybe the natural potential function would have been just x squared plus y squared. But then if we try to prove the lower bound, then the allocation of beads from now on after the next cut will have to be proportional to a vector with possibly negative coordinates. So somehow we have to make sure that the coordinates of this vector are positive. And you remember that we already said that we may assume that x and y are at most m to the 2/3. And because of this vector here is always positive, and we can indeed allocate beads according to these ratios. Okay, so this is what we do. And then it turns out that you do some computations that I'll not show. And cutting after a segment containing z beads, then it increases m by at least z squared over 2 minus some correction. The correction that I wrote here is 3z minus 5m to the 2/3. So if z is very small, then maybe it can even decrease the potential function. But if z is somewhat big, then it already increases it. Okay. So if we believe this, then after adding all these m beads, let's say m of our beads, we have m beads of each type. So as long as I'm adding only m beads, I don't have any restriction. I have beads of any type that I want. So if I'm using only r cuts, then the value of this potential function, by what I said before, will increase by Cauchy-Schwarz or something, will increase by at least m squared over 2r minus what accumulates from all these error terms. And this is negligible if r is small. If r is a small fraction of m to the 2/3, then this will tell us that the potential function is bigger than 8m to the 4/3. And this will force either x or y to be bigger than m to the 2/3. And as we said already at the beginning, once x or y are bigger than m to the 2/3, then we are done. So this is modulo some computation. This is basically how it goes. And let me just finish with a few problems. So one problem is what is the best epsilon that we can hope to achieve efficiently if we use exactly k-1 times n cuts for the approximate version, right? So as we said, for fixed epsilon k equals 2 and large n, this is PPAD hard, but maybe for some epsilon, so here are two comments about it, both are easy. The first one is that if the number of types is only 2, right, and now I allow k to be, the number of fifths can be arbitrary, but there are only 2 types, then even epsilon equals 0 is simple, so we can get it completely exactly and efficiently. And this is basically the fact that the Borsuk-Ulam theorem for S1, for the one-dimensional sphere, is just the intermediate value theorem, which is essentially efficient, and this gives the way to do that. And we also have a relatively simple argument that for every nk, we can at least ensure a positive number of beads of each type to each agent, and in fact, even online with the right number of cuts, but this positive is very small. So it's 1 over nk. It goes to 0 when the number of types goes to infinity. Then there is some small gap, but maybe it's interesting to close it, some logarithmic gap about the best possible number of cuts for an online algorithm for the exact necklace halving. So again, I want to split it exactly with n types. each appearing m times. In the upper bound that I didn't show, there appears some small power of log, and in the lower bound, so it behaves like m to the 2/3 times the number of types, but there is this logarithmic term. And the last question that I want to mention, which should be easy, but for some reason we didn't see how to do it. So somehow in the online model, if we have only 2 types of beads, then in the argument, as I showed you, we need for the lower bound, it seems that we need the 3rd type, but we couldn't improve the upper bound also. So what is the truth for 2 types of beads, each appearing m times in this online model, right? So the upper bound is m to the 2/3, the lower bound is only m to the 1/2, and maybe the truth should still be m to the 2/3, but it would require some modification. We don't see how to do it. And with this, I'll finish, but let me show you. So the relevant picture is that actually, and this is something I observed only a few years after we had all these proofs of the necklace theorem, is that in fact, the original case k equals 2 of the necklace theorem can be really proved from the hem sandwich by a few lines, by just viewing the necklace as a hem sandwich. And I'll not say more, and I'll let you try to figure out what exactly this means. And with this, I'll finish. Thank you.
Thank you. Questions, anybody? I have a question. So I've got a little mixed up with all of the results, but so in the online setting for the case of 3, was the upper, did you say that they had a matching upper bound?
For the 3 types, and there is a matching upper bound there. So up to a constant factor.
And does it somehow follow the 3rd case of the lower bound, or?
So it's basically by looking at an appropriate potential function and by deciding how to cut, just making sure that every interval that you cut does not contain too much of each measure, and then allocating it in order to keep the potential function small.
I see. How did m to the 2/3? I didn't quite see where that came into the.
Right. Yeah. Sorry. And so you do this up to some point, and then close to. So basically, you think about epsilon as 1 over m to the 1/3, and you keep the discrepancy between what guy 1, guy 2 have to be at most m to the 2/3. But you stop it when you are close to the end. So when the number of beads of some type is less than m to the 2/3, then from then on, each bead of this type you will cut before and after it.
I see.
Just give it to the right. So up to a point, indeed, we use the potential, and then at some point, which can come earlier for some types and later for some other types, we start cutting them at every point.
And one other question. So when the normal problem, the offline problem, for when n is 3, what's known? Is that when it becomes hard, or?
Right. So when n is 3, but k has to be big then, right? Because if k is also small, we just check all possibilities. When n is 3, it looks that it's already hard, I think. I mean, so it's so the proof is basically some version of Borsuk for from functions from S2 to R2, and and it looks, or at least I don't know anything that is special for 3.
Mm-hmm. Thanks. Anybody?
I have another question. In the online case, if you you can cut anywhere, you don't have to cut right before it, you can cut anywhere in the middle of the last bead. Would that break the lower bound?
No, so you're saying that if I'm allowed to cut in the middle of a bead.
Yes,
Yeah,
specifically the last bead.
Yeah, it will not change. It will not change anything, basically. Yeah, because it's it just. I mean, we anyway have this rounding lemma that tells you that when you cut, you are not distributed exactly as we want. So again, you will cut and you will have some half somewhere, but it only. Yeah, so it does not even affect the constant. It just it will stay the same. And in fact, right. So in some sense, the basic lower bounds holds for general probability measures. If you want to get an epsilon approximation for the exact necklace, you have to worry at the end also about these things that Tony asked about the end of it, but it basically, the argument applies to any probability measures.
Noga, I wanted to ask about approximation algorithms.
Okay.
What can you say about approximating the optimal number of cuts for a given necklace?
Right, yeah, so that's another question that makes sense. Of course, we were talking about finding k-1 times n cuts, which is the guaranteed optimum in any case, but there is also the question of finding the optimum number of cuts, and for some specific necklaces, maybe we have a small number of cuts. And so the only thing I know, I mean, it's pretty easy to show that finding the minimum possible number of cuts for which this is possible is NP hard, NP complete, yeah, definitely it's in NP. And I don't know about approximation. So I don't know if people thought about it, but and maybe it's interesting. So to try to approximate the optimum, which may be much less than k-1 times n.
Thanks.
But I don't.
I have a question. It seems very generous to let the online person who's distributing the beads know what cuts were made by the thieves. Is there a way of phrasing a question where that doesn't happen? I understand if just the standard question, it's not going to work, but could you like let the thieves have a finite collection of strategies and ask them to that they get to use the result of their best strategy, for example, or something like that?
So you want to get to restrict the way the thieves can do. So they are only allowed to
restrict the way the person who's distributing the online beads is allowed
to restrict the way of distributing
the online before the thieves decide their strategy in some way.
Right. So yeah, one can think about randomized algorithms, for example. Maybe this is but yeah, I don't know. I mean, maybe there is also an interesting version in which you restrict the way the beads are allowed to appear, and then maybe things will be better for the online. Yeah, I don't know what would be a natural formulation of the problem. Okay. But yeah, but it could be, and right.
You could let the thieves specify a finite collection of strategies, for example. 10 strategies.
A finite collection of possible
algorithms.
But again, algorithms for distributing the beads.
For the cuts.
For the cuts, right? So we will specify the cuts before we see the necklace or after?
Algorithm, a collection of algorithms to distribute the cuts.
Which means that we will be restricted in the way we can do cuts, or we will be restricted in the way we can distribute the beads?
Well, they have 10 different functions from the beads to the cuts, basically.
Okay.
Then the online person chooses a collection of beads, and then the thieves apply their 10 different functions and they take the best one, for example. I mean, I don't know, that's possible.
Okay, I see. But this means that you give the thieves even less power, right? So they are not allowed to do anything. They are allowed to, or you mean they specify algorithms, and then you get the whole necklace, and they are allowed to use one of them.
Their algorithm only has to be online, but the person who's distributing the online beads is not allowed to know which algorithm they're using. That's the idea.
Yeah, so guys,
okay, I see.
a guy says on the Zoom chat that maybe the question is about randomized cutting algorithm, the adversary is oblivious.
Yeah, so
or
it could
somewhat
be,
oblivious.
right. Yeah, but I understand. I mean, basically, when you have potential function arguments, you can take this. If you don't have too many algorithms, you can take the sum over all of them. But yeah, but I'm not okay. I'm not sure. So maybe there are some interesting questions here. Right. Okay. I keep following the number of people, so I'll stay until there are, as long as there are, I don't know, 10 people.
I will stay until the meeting ends.
Okay. But, right. Yeah. Yeah, because in these Zoom lectures, you never know when it really ends, right?
That's the fun part. You watch the number go down, and you wait,
so
and you stick around to see who stays to the end.
Yeah, you have to decide, right? Okay.
So Noga, I don't like this because the ham sandwich is supposed to have just two bread and one ham, right? It's not supposed to have all these other things on it.
Right, yeah, I took from the internet what I found, but there are other versions as well.
Yeah, so this guy Steinhaus, he named it the ham sandwich theorem, which is funny, but whatever.
Okay, yeah, and it's
Noga, if you don't know, you know that a cut has been made, but you don't know who gets the cut, the interval. Does it make any sense in the only case?
So what does it mean that I don't know? So as an adversary, you mean they make a cut? Yeah, so it makes sense. I mean, we thought a little bit about things of the form that you, in one pass on the necklace, the algorithm makes all the cuts, and then given everything, it's he allocates the intervals to the thieves.
Yeah, that's the same.
And then it can improve the situation, indeed. So you can then you can use some of the results about discrepancy now without extra cutting will apply to this thing as well, and you get somewhat different behavior. And maybe even maybe one can think about algorithms that make a constant number of passes on the necklace and are allowed to still modify things a little bit, maybe to add cuts and yeah, but right.
Thank you.
Okay, thanks.
Noga, just a remark. Edgardo Roldan Pensado and Pablo Soberon have just put on the archive a paper called A Survey of Mass Partitions.
Okay.
In which they talk about the necklace problem and some other problems, which could
Right,
also
yeah.
work for complexity purposes.
That's right, yeah. So there are other problems that I didn't discuss here, and there are quite a lot of recent papers, mostly about hardness. So the other problems deal with measures, with general measures, and we want to split it. Sometimes it's not even additive measures; it's just functions, and you look at the integrals and also in the cake partition problems, sometimes you don't want to be fair completely with respect to all measures, but you just want that each agent will be happy with respect to his or her own measure. And so there are many other versions, and there are hardness results for some of them, and not for some others, but so and thanks. And I think I haven't seen this survey, but I've seen several recently.
I posted a link in the chat.